Hi, I'm Josh Hassim, and my PhD project is low-cost sensing of aerosols, sensor development and integration for first and second moment measurements. Air pollution kills an estimated 7 million people worldwide every year. Current legislation mandates measurements of PM2.5 and PM10, but there is a drive to measure particles below the optical range, which is diameters less than 300 nanometers, as well as in the ultra-fine region, which is diameters less than 100 nanometers. Ultrafine aerosol particles are known to be a major risk to human health due to their high number concentrations and ability to penetrate deep into the human lung. However, evidence of the health effects of ultrafines from local sources is limited owing to the sparse availability of appropriate sensors allowing for monitoring of particles in this size range. Current methods for ultrafine detection often rely on expensive, complex, large benchtop systems or low-cost sensors which only provide accurate measurements for controlled sources. My project will look to develop sensors that can measure aerosol particles in the fine and ultrafine size ranges. The two main sensors I will be working on are shown here in Figure 2. On the top is the bipolar charging sensor, and on the bottom is the UV photo charging sensor. The bipolar charger ionizes gas molecules using a radioactive americium-241 source. These gas molecules then diffuse and collide with the aerosol particles, creating a steady-state charge distribution. This sensor provides a current signal which is proportional to the first moment of a particle size distribution, that is, the product of number concentration and arithmetic mean diameter. The photocharger ionizes the particles directly using UV light. Photons collide with the particles, causing them to eject electrons. This charging mechanism produces mainly positively charged particles. This sensor has been shown to have an outlet current proportional to the second moment of the particle size distribution, which is total particle surface area. Significant work has already been undertaken on the photocharger, which has investigated the physics behind the photocharging process, as well as the effect of particle morphology and aerosol polydispersity on the sensor response. The bipolar charger has been shown as a proof of concept device and has shown good agreement with more mature technologies. A combination of both experiments and computational modeling will be used to investigate and further develop both charging sensors. A previously developed CFD code will be used to optimize and develop the geometry and source placement for the bipolar charger, such that a steady-state charge distribution is attained and the total radiation is minimized to below current exemption limits. Experiments will be conducted for both controlled laboratory and ambient conditions to investigate the effect of environmental factors such as carrier gas composition, relative humidity and temperature, as well as the effect of material and morphology. Experiments will also be conducted with other low-cost sensors to determine whether an array of sensors can provide a more complete measurement of a sampled aerosol than is possible with a single sensor. Thank you for listening.